Hi students, welcome to my lectures on chemical reaction engineering. In today's lecture, we are going to discuss various aspects of elementary reactions, non-elementary reactions, order of the reaction and molecularity of a reaction. Yes, and we start with element because the elementary, most of the chemical engineering reactions are non-elementary in nature. The non-elementary is a bit difficult to interpret. Elementary reactions are those where we can straightforward get the informations of rates, molecularity and order. For non-elementary reactions, we have to go through a bit separate process. When it comes to the elementary reaction, let us start our lecture. For example, A moles of A plus B moles of B gives rise to C moles of T plus D moles of D. And rate of reaction for elementary or non-elementary reactions is generally represented by minus RA is the rate of reaction of A is nothing but rate const Ka into concentration of A power alpha and concentration of B power beta. So, rate of reactions generally depends on the concentrations of the reactants or the concentrations of the products. Okay. More is the concentrations, and if you see, and rate is directly proportional to the concentration power alpha, that means A power concentration of A power alpha and concentration of B power beta. If this is the thing, more is the alpha and beta, that means the rate depends on the concentration of A. More is the concentration, more is the rate. More is the concentration of B and more is the rate. That means if alpha is higher and beta is higher, that means the dependency of the speed of the reaction will be higher. If you give more concentration of A in the reactor and more concentration of B in the reactor, the rate, the speed at which the reaction happens will be higher. Ka is kind of a rate constant of this particular reaction, which is a proportionality constant you can talk about. The Ka only depends on temperature. Okay. If this is your rate expression, then how can I say whether it is elementary reaction or non-elementary reaction? So, I have given a very simple, small, concise definition. Rate of reaction can be related to the stoichiometry, then it is a elementary reaction. What this means is, when you see the rate expression, the concentration power concentration of A power alpha and concentration of B power alpha, this alpha beta can be related to the stoichiometry coefficients, then it is an elementary reaction. Example, you can see the stoichiometry coefficient of A is A and the stoichiometry coefficient of B is small b, and if alpha A equal to alpha and B equal to beta, that means alpha equal to A and beta equal to B, that means which can be related directly to the stoichiometry of the reaction, then it is called elementary reaction. That means I can represent this equation minus Ra is equal to rate constant of A, which is Ka, into concentration of A power A and concentration of B power B. You can see now it can be related to the stoichiometry of the reaction. Then I can say then whatever the reaction which is shown here is called elementary reaction. Elementary reactions are simple to deal with. You can define order and molecularity of a reaction in a very concise way. Okay, what is the, let us see some examples first. 1 mole of A is giving 1 mole of B. Then what is my rate of reaction of A is rate constant of A into Ca power 1. This one and this one is getting matched. Okay, that means it is an elementary reaction. 2A gives rise to 2B. Okay, another example, minus Ra is equal to Kca square. You can see 2 and 2 is getting matched. Okay, you cannot cancel these two. Don't do that, because two molecules of A should come together for the reaction to happen. So, that is why you cannot cancel these 2 and 2 and say A equal to B, A gives rise to B, you cannot do that. From the experiments it says that rate is proportional to concentration of A power 2 Okay, that means you have to represent the equation in this way. Okay. Here if it is experiment says that rate of reaction of A is Ca power 1, then you can 1A gives rise to 1B you can write. Okay. But whenever from the experiments you can figure out that the speed of reaction is proportional to the concentration A power square, then you have to represent the equation in this way, 2A gives rise to 2B. Okay. And third, 2A plus B gives rise to 1C plus 1D. That means minus Ra is equal to rate constant of A into Ca square and Cb power 1. Okay. Now 2 and 2 getting matched, 1 and 1 getting matched. Here also it is 1 mole of P. Okay. Then you can say it is called elementary reaction. The thing is, what is the order and what is the molecularity? Now you have figured out, okay, this is an elementary reactions, these examples. In these 3 examples, how to find out what is the order of the reaction and molecularity? Order is sum of the powers of all the all the coefficients in the numerator in the rate expression. Example, here the order is 1, here is order is 2, here the order is 2 plus 1 which is 3. You have to add together all the powers of the concentrations of all the molecules involved in the rate expression. Okay. What is molecularity? The molecularity is number of molecules involved in the reaction. Okay. You can see these are the rate determining steps. Okay. Let us talk about the rate determining steps in the non-elementary stage. Okay. What is it that? Number of molecules involved in the particular reaction. Here only one molecule of A is required to form B, then molecularity is 1. That is why order is 1, molecularity is 1. A number of molecules involved in the reaction, 2 molecules of A. That is order is 2 and molecularity is 2. Okay. How many? What is the order in this particular reaction? 2 plus 1 which is 3. What number of molecules involved in this reaction? 2 and plus 1, 3. Molecularity is 3. So this is the way, and not because always keep in mind order does not necessarily equal to the molecularity. Okay, or molecularity number can be different and order number can be different. In these examples we have cited, and fortunately that both the numbers are same, and in reality both the numbers doesn't necessarily equal the same. So in very simple sense, elementary reactions are those where I can relate the stoichiometries and concentration powers in the rate expression. If both are matched, then it is called elementary reactions. Let us go to the non-elementary reactions, because you have to a bit careful while I am teaching, because more difficulty come in play now. Non-elementary reactions. Example, H2 plus Br2 gives rise to 2HBr, hydrogen bromide. Okay. If this is the reaction, what will be the my rate of formation of HBr? Okay, is nothing but K times some constant of A. That means remember it is some rate constant into concentration of H2 power 1, concentration of Br2 power 1. If these both getting matched, then it is a elementary reaction. But this reaction is not an elementary reaction, this reaction is a non-elementary reaction. From the experiments it is found that the rate of formation of HBr is nothing but K1 into concentration of H2 into concentration of Br2 power 1 by 2 divided by K2 plus concentration of HBr into concentration of Br2. Nowhere you can relate the stoichiometry and the concentration powers. So if you see the mismatch here, then you can come to a conclusion that it is a non-elementary reaction, because I cannot be able to relate the concentration powers and the stoichiometric coefficients. And whenever non-elementary reactions means reaction won't be a single step. That means this reaction happens in 2 or 3 more steps are there. Because of the more than one step is involved, you cannot relate the stoichiometric coefficients and the concentration powers. There are number of ways the non-elementary reaction happens. Mechanisms are existing. One such a few mechanisms are ionic reactions or chain reactions, in which the free radical will form. Okay, if those kind of reactions, more than one step is required to go to the product. Okay, whatever this reaction happens in multiple steps were listed here. Okay, reaction happens in 3 different stages. First, initiation happens, propagation happens, termination happens. These are the 3 different steps that is involved in this free radical mechanism. First of all, the Br2 gives rise to 2 Br dot, dot means free radical. This is called initiation step. Next, Br dot, that is the free radical, reacts with hydrogen to form HBr and free radical of hydrogen. And this free radical hydrogen reacts with the Br2 to form HBr plus free radical of hydrogen. These 2 reactions are called propagation reactions. Why this propagation? Because of these 2, the HBr will continuously going to get formed. Here only free radical is going to get formed, which will initiate the formation of the product, which is HBr. That's why it's called propagation reactions. And finally, the chain has to stop. 2 Br dot gives rise to Br2, termination reaction, because 2 free radicals comes together to form 1 Br2 molecule. When 1 Br2 molecule is there, then no more reaction is going to happen. Reaction is going to happen because of the Br dot. Br dot, as long as Br dot is there, the reaction will continue to proceed. So, 1 initiation reaction, 2 propagation reactions and 1 termination reactions. Then how you can define order and molecularity of these kind of reactions, which happens in more than one step? From the experiments, it is found out, if you want to define rate or molecularity, okay, then you have to find out among these 4 reactions which one is the slowest one, because always the slowest one decides how fast a person can go. Even let us example in the first case, first reaction happens very fast, second reactions very fast, fourth reaction very fast, only the third reaction is very slow. Even though 3 reactions are fast and 1 reaction is slow, because of this one step, even though these 3 steps are fast, because of this one slow step, reaction will go slowly. So, the speed of the reaction is ultimately decided by the slowest step in among all the reaction steps. And from the experiment is found out the step number 3 is a rate determining step. That means that is the slowest step which determines the speed of the reaction, that is called the rate determining step. So, from this you have to once you identify which one is the rate determining step, then you can define molecularity of this particular reaction is determined by this slowest step. That means locate the slowest step, identify how many molecules are involved in this particular reaction, that will give the molecularity of this particular reaction is 2. Okay, you don't need to worry about the other reactions. Find out which one is the slowest step. From the slowest step, identify what is the molecularity. Okay, now we have found out the molecularity. Then you have to find out order. Here you have easily found out the order is sum of the powers of the concentrations. Here, if this is the scenario, you cannot define the order of the reaction in a very simple way, because order is different at conditions. I mean, because same reaction will show different orders at different conditions. For example, I take this equation, let us find out the order of this non-elementary reaction, and at low concentrations of Br2. Okay, I told you order will be different at different conditions. Let us take one such a condition where the low concentrations of Br2. What happens at low concentrations of Br2? Take this equation, take the denominator here. Okay, K2 plus H as concentration of HBr into concentration of Br2. Because I have already figured out that, but I am conducting a reaction at low concentrations of Br2. In such cases, CHBr into CBr2 is close to 0 because low concentrations. That means the entire denominator K2 plus CHBr into CBr2, which is closely equal to K2, because it is negligible now. Okay. Now, let us replace this denominator with only K2. That means rate of reaction of HBr is equal to K1 CH2 CBr2 power 1 by 2 divided by K2. K1 is one rate constant, K2 is another rate constant. Let us put K1 by K2 is Kn, which is new rate constant. Now the entire equation will become Kn into CH2 power 1 CBr2 power 1 by 2. Now you can define the rate. Okay. What is the rate at low Br2 conditions? Means 1 plus 1 by 2, which is 1.5. The order of this particular reaction at low concentration conditions is 1 plus 1 by 2, which is 1.5. Okay. Let us take another condition. Okay. At high concentrations of Br2, that means take the denominator K2 plus concentration of HBr and concentration of Br2. What is happening here? I told you that Br2 concentration is very high. That means compared to K2, this term will be very high. That means no, K2 will be now negligible compared to this particular term. When such a case happens, you can neglect K2 now. Now what happens? This entire denominator K2 plus CHBr into CBr2 is close to, you neglect this, then CHBr into CBr2. Now put this denominator again in this rate expression. That means rate of HBr is equal to K1 CH2 CBr2 power 1 by 2 divided by CHBr into CBr2. Now you can take everything to the numerator and cancels out, and K1, that means CH2 power 1, and if you take to the numerator CHBr power minus 1 and you take CBr2 to the numerator, that is minus 1, 1 by 2 minus 1 will give you minus 1 by 2. Now you measure the order. The order of this reaction at these conditions, 1 minus 1 by 2, which is minus 0.5. The orders can be fraction, orders can be negative. So these are one such case you find the rate of reaction, order of the reaction is negative. I hope. See the same reaction which shows the rate, look at this rate expression which comes from the experiments. 1 at low conditions, it is low Br2 conditions is given 1.5, at high bromine condition, Br2 conditions, which is minus 0.5. That is why in elementary reactions you cannot get the order of the equation or molecularity of the equation straightforward, like the case of elementary reactions. For non-elementary reactions, you have to go through, as that's why it is defined. Order is different at different conditions. Molecularity, you have to identify the rate determining step. In this rate determining step, you have to identify how many molecules are involved in the reaction. Then the molecularity is 2. Hope you get the clarity on elementary reactions, non-elementary reactions, and order and molecularity. Thank you. We will meet up with a new lecture.